because they're dry, they're themselves explosive. Okay, so things just trigger off the nitrogen extrusion. But if you keep this in solution or wet suspension, these guys are sufficiently stable at room temperature that you can isolate them. Okay? And the reason for that is, first of all, resonance. So the electron pairs of the benzene ring can resonate into the N-N triple bond, and you typically write that by moving an electron pair out onto this nitrogen, making it negatively charged, and invoking the benzene ring, so this kicks in. So you get a dipolar structure on top of this plus charge, which stays untouched, where the plus charge can whiz around that ring down here. Okay? So there's some resonance that stabilizes it. And the other reason is that when the nitrogen takes off, it leaves behind a cation that is much worse than an alkyl carbocation. It's a cation that's sp2 hybridized. And so it's reluctant to leave because it leaves behind something really bad. Or you can turn this around and say the phenyl ring hangs on to the nitrogen because it doesn't want the nitrogen to leave because it would become a very unhappy camper, namely a phenylcation. This phenylcation is so unhappy because the plus charge is sitting on an sp2 hybrid, and that hybrid is perpendicular to the pi frame of the benzene ring. We mentioned this before, but I'm rubbing this in. So it's not delocalized into the benzene ring. It can't overlap with the benzene pi orbitals. And to drive this home, one can draw a molecular orbital picture where you can see clearly the pi frame of the benzene ring, and you can see that the plus charge is sitting in this sp2 hybrid that is perpendicular to the pi frame. Once it's formed and you can make the nitrogen leave, all you have to do is warm up these solutions. So room temperature, they're fine. You warm them up to 80 to 100 degrees. At around 80, the nitrogen starts bubbling out. And you can visibly see this actually in solutions. And you can control it, making it dilute enough that it doesn't explode. And once the phenylcation is formed in the aqueous medium, water immediately traps it. Okay? And that was a phenol synthesis that we discussed as part of our synthetic palette for making phenols. Okay? Now it turns out that you can, maybe not surprisingly, can trap the phenylcation with other nucleophiles. And one of them that you can do without any further manipulation is iodide. Iodide is a much better nucleophile than water, so even in aqueous solution, the water the iodide completes the water to trap the corresponding phenylcation. So if you start from this and you run the sodium nitrite acid reaction in the presence of HI, and you run this such that you already warm it up, so you can do all of this in one step. The diazonium salt is formed, and 2 blows off. You get a plus charge here. Iodide traps it. So we can form an iodo-benzene, an iodo-arene derivative. Now, this is actually a very useful transformation because it's the only way that you know of how to make readily, by substitution, by direct attack, iodobenzenes. You may or may not remember, we briefly mentioned it and then it never was mentioned again, direct iodination by electrophilic aromatic substitution with iodine and Lewis acids, let's say, doesn't work because it's endothermic. Okay? We mentioned this and then we dropped it. And so you may, in retrospect, recall that all of the other electrophilic aromatic substitutions we did with halogens were bromine and chlorine. Okay? Fluorine is too reactive, and it's explosive if you use fluorine, so that you stay away from that. So we did just chlorinations and brominations, and we never touched iodination. The reason is, when you look at the bonds broken and the bonds made in electrophilic iodination, the bonds broken, the sum of the bonds broken is larger than the sum of the bonds made. So it's endothermic, and so this is a neat way around that, actually, to go through the corresponding benzene amine. Remember, the amine, of course, can be derived by nitration, so ultimately it's a roundabout way of doing electrophilic iodination in a stepwise manner. Nitrate, reduce the amine, make diazonium, and then heat it up with under these conditions where you make nitrous acid and HI. You can use other nucleophiles, and it turns out that it's best in these reactions that you use, for these examples, that you use copper catalysis. So actually what this indicates is that the mechanism slightly changes. It's suspected to turn into an electron transfer mechanism where you have radicals involved. We won't go into that, but this is a necessary ingredient, in part because the nucleophiles here are not hot enough otherwise to outcompete water in the mixture that makes a diazonium salt. So you do need to have copper plus. So you use copper salts with the corresponding nucleophiles attached. In this way, you can make chlorides. So again, amine, diazonium, you take cuprous chloride, CuCl, so that's copper 1, copper plus. Notice 60 degrees, quite mild, you get the chloride. Okay, big deal, we know how to do electrophilic aromatic chlorinations. But remember, this position of this chlorine, we couldn't make this directly from methylbenzene, okay? So unless you block the power position. So it gives you an extra flexibility with respect of putting nucleophiles where you want them. You use cuprous bromide, you get the corresponding bromide. This was done at 0 degrees, this was done at 100 degrees, so boiling the mixture. And again, this is in principle doable by electrophilic bromination if you mess around with the strategy of blocking and putting the bromine next to the chlorine. Much more interesting in many respects is this one, where you use cyanide, because there you make a carbon-carbon bond. Okay? And that you definitely couldn't do by electrophilic aromatic substitution, to introduce a cyanide group into a benzene ring. And that is, of course, useful because it's part of organic synthesis to make new carbon-carbon bonds, and we now know how to use nitriles for all kinds of transformations. As you know, it's a masked carboxylic acid function, so all the carboxylic acid chemistry can be brought in here, but you can also, of course, hydrogenate to the amine, and lithium dibol will take it to the aldehyde, and so on. And finally, there's another rather neat reaction. You can remove the amine quite effectively by a reducing agent. So you take the amine, turn it to the diazonium, and then you treat it with H3PO2, which is a weird beast. It's the lowest oxidation state phosphor acid that we have encountered so far. Remember, the normal phosphor acid is phosphoric acid, H3PO4. That's the acid that makes all the phosphates that are abundant on this planet. That's the highest oxidation state for phosphorus. We have seen H3PO3 as the hydrolysis product of PBr3, when we use PBr3 to turn an alcohol to a bromoalkane, for example. That's already a lower oxidation state species. And then if you take another oxygen away, it's H3PO2. The structure actually is here. Okay? And this is a reducing agent. Phosphorus wants to be in a higher oxidation state. So it gets oxidized by the phenylcation, or to put it differently, you can view it like a phosphorus-based borohydride reagent, because it acts by donating hydride and trapping the phenylcation with H-. And that reduces the benzene ring to the parent system, and you get a P plus charge here, which is trapped by water, so that adds hydroxy here, and that is nothing else but H3PO3. So it's oxidized to the phosphorus acid. So this is a piece of vocabulary to remember. H3PO2 reduces this to this proton. And that's also very neat because that gives you another handle with respect to blocking groups or directing groups that you want to remove after they've done their job. So you can introduce amine via nitration, turn it to the amine, let it do its job, namely ortho-para directing. And then, if the product doesn't show that nitrogen on the benzene ring, you can get rid of it after it's done its directing job. And this is the way to do that, via the diazonium cation to make the corresponding species. So strategically, this is an extension of chapter 16. It allows you to do even more than you already know with respect to selectively introducing substituents. So generically, you can start with some arene, substitute benzene. You can nitrate, turn the nitrate into amine. The amine, you can use the amino group as a directing group to introduce halides and alkyl groups and nitro groups and what have you, and then make the modified amine, and then you get rid of the NH2 group to go back to now the specifically functionalized new arene. So you turn this eventually into that via this particular sequence. In addition, what we've learned is that we can turn an arene into a nitro into the amine and replace amine by nucleophiles. The nucleophiles are OH for phenol synthesis. They're iodides, chlorides, bromides, and cyanides. Okay? Let's have a break. Okay, so we started today with an extension of electrocyclic reactions. We continued in some aromatic chemistry using and looking at the chemistry of benzene amines. And now in this chapter, we're just going back to carbonyls. And what we're doing here is an extension of what we have learned with carbonyl chemistry to develop chemistry of dicarbonyl compounds. Some basic chemistry of dicarbonyl compounds, which has given rise to some exceedingly useful additional transformations that you can use in synthetic applications. And the first one is actually, since we are on the theme of Claisen today, is the so-called Claisen condensation. So this is another reaction that Rainer Claisen discovered, which is essentially the ester variant of the aldol, at least in its initial reaction step. So remember the aldol addition. So I'm starting this by reminding you how the aldol works. The aldol was a reaction where we took an aldehyde or ketone with base, and it was done, it can be done with stoichiometric base, or we did it most of the time just catalytic base to set up the keto-enolate equilibrium. So you deprotonate, make the enolate, higher energy, endothermic, but you pull the equilibrium by trapping the enolate that is formed by deprotonating, so this is done for acetaldehyde, with the surrounding excess of starting material by nucleophilic addition. Okay? So after the addition, you have the O-, the O- is trapped by protonation. And that was the first stage of our aldol condensation, the addition step. Okay? In the case of aldehydes, you may or may not remember, this was actually slightly exothermic because aldehydes are quite reactive. In the case of ketones, this step is actually slightly endothermic. Okay? And we didn't care much about that because typically we use the aldol reaction in the aldol condensation. That is, we followed up by heating to eliminate water and put in the double bond here. Okay? But it's this initial step that I'm now going to apply to esters and ester enolates. And that is the so-called Claisen condensation, which is in fact, strictly speaking, not a condensation because condensation implies elimination of water. It's sort of because you're eliminating alcohol. Okay, so what you do is you just take, instead of taking an aldehyde or ketone, you take an ester. And you expose it to the same types of conditions, namely base. You need to have, actually, as it turns out, stoichiometric base. We'll find out in a minute why. And set up an equilibrium between the starting material and the corresponding enolate. And so when you do this, you use a base, and notice that the base that's used is not sodium hydroxide, for example, because sodium hydroxide would hydrolyze the ester to the corresponding carboxylic acid. You need to use an alkoxide. And what you need to do is use an alkoxide that is based on the alcohol that is part of the ester. Why? Because by far the fastest reaction is nucleophilic addition elimination. Okay, rather than deprotonation. Okay? That's always fast. Okay? We've learned that already before. Okay, so if you use a different base, a different alcohol base here, like sodium methoxide, methoxide will exchange or will kick out the ethoxide and turn this into the methyl ester. If you don't care, that's fine. You can use methoxide. But typically, people use the alkoxide that's based on the ester piece of the ester function. And out comes this. Actually, not quite this. Actually, what comes out is the anion, because this CH2 group is acidic. And this is the crux of this process, because as written, this plus that, giving you that, by making the enolate and doing addition elimination, is actually endothermic. Okay? So it's similar to the aldol addition of a ketone, where the addition step is endothermic. This step, addition elimination, is endothermic. The reason that this works is because this CH2 group is acidic. So you use actually stoichiometric amounts of base to, once this is formed, to deprotonate it, and that drives the equilibrium all the way forward to the corresponding anion, and then you work it up with water, and you get the species here. Notice that this is very useful transformation because it makes a dicarbonyl compound, specifically actually an oxoester. Okay? And you start with any ester that you want. You can have substitution here, so I'll just use methyl to give correspondingly substituted products. So the mechanism of this, to do this step by step, I'll do on the board, involves indeed in the first step the deprotonation of the ester. So I'm going to do it for a methyl ester. Saves me some writing. And this reacts with the base, and so now I have to use methoxide as the base. Otherwise, I get transesterification. Let me rephrase that. Transesterification is occurring, but when you use methoxide, it gives the same product. So it doesn't change the ester function. Transesterification is way faster than deprotonation. Okay? So it goes in, out, all the time. Every now and then it deprotonates. So I'm just going to write the deprotonation step to make the corresponding enolate. That's the ester enolate. And the ester enolate then attacks, which is high energy, it's formed in minuscule quantities. It's surrounded by starting material, so it attacks starting material. So this electron pair kicks back out, and this attacks here. Addition. That gives you the addition product with methoxide having added. Sorry, not methoxide. Enolate having added. And we have our leaving group here, since this is an ester. So the electron pair kicks back in and kicks out the leaving group. And the net result is the oxoester. Now, all of this is reversible. And as written at this stage, this is actually still higher in energy than the two starting materials. What drives the reaction is the last step, which is the deprotonation of the relatively acidic hydrogens that are sitting between the two carbonyl functions, which on deprotonation give you a super stabilized enolate, stabilized twice by two carbonyl functions. So if we write this, actually I should write it going this way. But it can go to either side. And that drives the equilibrium, Le Chatelier's principle, all the way to product. And once you're done, you dump in water and trap, and you isolate the neutral product, which is your Claisen condensation product. So this is an extremely simple reaction. It's an addition elimination using an enolate as a nucleophile, rather than we've learned to do this with hydroxide and with amides and the like. Now we're just using another nucleophile, and it's directly related to the aldol addition type reaction. So these guys are relatively acidic, as I mentioned. In fact, the pKa is around 10. And we'll look at related species and discuss why they're acidic in more detail in a second. But there's a movie that I wanted to show you of the Claisen reaction. And so here it is. Here's the acidic proton. Ethoxide. So this is now an ethyl ester. So ethoxide removes the proton. You get the enolate. This carbon is now sp2 hybridized. You can see it in the molecular model. And it's surrounded by unreacted ester. So you get addition. And then followed by elimination. At this stage, you are actually endothermic, but it's driven by the last step,